Read the question carefully. We need to set up the initial value problem. First, let's find the ingredients. We know that for mass spring problem, the initial value problem is m u double prime plus gamma u prime plus ku equals the external force, and we have initial displacement some value and initial velocity some value, let's say v naught. Okay, let's find m, that's the mass. So in this question, mass weighing 10 pounds, that's the weight. So we need to divide this by acceleration due to gravity, which is 32. 10 over 32 is 5 over 16, that's the mass. Stretches a spring 2 inches. So the stretched length of the spring, which is uppercase L, is 2 inches. We need to convert this into feet, divided by 12, so 1/6 feet. Now if the mass is displaced an additional 2 inches and is then set in motion with an initial upward velocity, so these are initial cases. So this is initial displacement, okay, 2 inches, and initial upward velocity, that's the initial velocity. So u0, initial displacement is 2 inches, and 2 inches is 1/6 feet, and initial upward velocity u prime 0, upward means negative 1 foot per second, just negative 1. Now we need to determine the position of the mass at any later time. Position means u. We need to find the function u in terms of t. Also determine the period, amplitude, and phase shift of the motion. So look at here, this k is spring constant. We can find spring constant by this stretched length. So as soon as you have the stretched length, you can find k. Okay, that's the weight divided by stretched length. Okay, weight is 10 pounds, or you can write mg, same thing, 10 pounds divided by 1/6. That means this goes on the top, so 60. That's the k. And here's gamma, which is the damping coefficient, and there is no mention of damping. That means gamma is 0. And there is no mention of external force, so ft is also 0. Okay, then we have the differential equation. We have the ordinary differential equation, m u double prime. So m is now 5/16 u double prime plus gamma is 0, so there is no second term, plus ku, and k is 60, so plus 60 u equals 0. Okay, ft is also 0. Let's solve this differential equation. 5/16, let me simplify this, and this is second order linear constant coefficient equation. We find the characteristic equation, and from there we write down the solution. Okay, let's find the characteristic equation. We can simplify this ordinary differential equation, multiply by 16/5 just to make 1, and this is the characteristic equation. Solve for r, we get these two roots. Then the solution is ut equals c1 cosine 8√3t and sine. Now we need to use these initial conditions to determine c1 and c2. And the second, to use the second initial condition, we need to find u prime. Look at here, u prime means we need to find the derivative. Okay, so let's find the derivative of this solution, and which is u prime is now cosine is negative sine, so 8√3 c1 sine 8√3t plus 8√3 c2 cosine 8√32 t. Now using the first initial condition, which is here, u0 equals 1/6 we get from the first equation here, u is 1 over 6 when t is 0. So c1 cosine 0. Cosine 0 is 1. So just c1 plus c2 times sine 0, because t is 0, sine 0 is whole thing 0. So c1 is just 1 over 6. Okay, and similarly let's use the second initial condition to find the second constant. So second initial condition is here. So using u prime at 0 equals -1, we get u prime, this is -1, equals look at here, sine t is 0, so sine 0 is 0, so whole thing is 0. Here we have now 8√3 c2 cosine 0, and cosine 0 is 1, so c2, that implies c2 equals -1 over 8√3. So we have c1 and c2. We go back here and plug in and find the solution ut. Okay, so thus the solution is ut equals c1, that's 1/6 cosine 8√3t, plus c2, c2 is -1 over √3 sine 8√3t. Okay, but we want to write this solution in terms of a single cosine function, so that we can find the amplitude, period, and phase shift. Okay, so we want to write this solution we have, where we have cosine and sine, into a single cosine function. To write down this into a single cosine function, then determine the frequency, period, etc. So we first find the natural frequency. So natural frequency omega naught, that was already found, square root of k over m, or we have here, if you go to the argument, this is it, 8√3. Okay, that's 8√3, and if you want to put in decimals, you get 13.856, about this radian per second, angle radian per second. That's the frequency. And next we're going to find the period. Then once we have the frequency, period is t, that's 2 pi over frequency, divide 2 times about 3.1419 by 8√3, you get about 0.45345 second. And next, the amplitude r is square root of these constants, c1 squared plus c2 squared. Okay, that's 1 over 36 plus 1 over 192, and if you use your calculator, it comes out to be about 0.18162, that's feet. And next we're going to find the phase shift of the motion. So delta is given by tangent inverse of, that's c2, because sine c2 divided by c1. So -1 over 8√3 divided by 1 over 6. Or our phase shift could be this plus pi. It depends. We need to determine the correct quadrant. Look at here, sine is negative and cosine is positive. Sine negative, cosine positive means fourth quadrant. And when we evaluate tangent inverse, we always get the answer either in first quadrant or in the second quadrant, sorry, in the fourth quadrant. So we are getting correct answer. Okay, if we were in like second quadrant or third quadrant, then we had to use plus pi. So use your calculator, and this gives you negative 0.40864. That's the radian. Okay, that answers everything. If you want to write down the motion in terms of r cosine, single cosine, then you can rewrite, but this is not asked. So ut equals the movement or the motion. Okay, in this case the displacement at any time t is r cosine omega t minus delta, which is now given here. That's 0.18162. Cosine omega naught we found here 8√3 t minus delta is negative, so this will be plus 0.40864. Final.